Hello, everyone. We'll start in about 3 minutes and wait for everybody to join. Thanks. Hello, everyone. Welcome to PSV 201. Is that Craig? Is that give me a nod if you can hear me okay?
Yeah, I hear you fine. Thanks.
All right, great. Thanks. It only seemed to make sense with the feedback with our introductory PSV webinar that we continue to that next level. So that today's webinar will be posted on Landmark's YouTube channel as well. So if you know of someone who missed out the session would like to see it, there'll still be access to it. If you would like that, just send me an email and I can send you the link. We'll be taking questions during the session today. If we don't get to you during the session, please hang on and we'll do continue to do questions and answers afterwards too. Now to get things started is that so our presenter today, I'm Mitch McLeod, Director of Business Development for Landmark Engineering. Our presenter today is Craig Stoll. He's a professional engineer and team lead with Process Landmark. Over 3 decades of experience in process mechanical engineering across oil, gas, petrochemical, industrial facilities. His background spans detailed design, process optimization, construction management, and strong focus on gas plants, oil facilities, pressure systems. Craig has led numerous overpressure risk assessments, HAZOPs, and PSV design, replacement programs ensuring compliance with codes such as ASME and API 520 and 521. Brings deep practical insight from both greenfield and brownfield projects, including facility debottlenecking, fire system evaluations, and complex process modifications. Today, he'll be sharing advanced perspectives on identifying credible overpressure scenarios and applying sound engineering judgment and relief system design. And with that, Craig, please take it away.
Thanks, Mitch, for the introduction and welcome everyone. like Mitch says, this is a continuation of PSV 101 that we did a few months back. So if you haven't seen that, hopefully this is, yeah, I don't think you'll be lost in this session, but essentially we're just going to do a deeper dive into some common PSV scenarios that we see in mostly upstream oil and gas. And with that, I'll just get started. So like I said, last session, we basically reviewed what is a PSV. So just as a reminder, its primary purpose is to protect life and property by venting process fluids from overpressuring piping and equipment. By code, PSVs are generally 15 psi or greater. And they're often the last means of protecting a system from overpressure and some kind of catastrophic failure potential. Today, we're going to focus a lot on API 521, and there's a section in API 521 about credible scenarios of overpressure. We're going to do a little bit deeper dive into that. Also, other codes like API codes that come into play with PSVs or API 526 and 527. They get into how PSVs are built, defining orifice sizes, and how they're tested. Also, things that can come into play are ASME boilers branch and pressure vessel codes, but we're not really diving into any of that today. And then we talked about the most common types of PSVs. There's conventional spring operated, balanced bellows, and pilot operated. They all have their, I guess, pros and cons and like where they're best used, which we went into last time. But I guess the most common feature of a PSV, pressure safety valve, is that it opens at the pressure, at its set pressure, and it reseats once that pressure in the system goes below the set pressure. Yeah, so common causes of overpressure. Today, like I said, we're going to go into a few common scenarios that we encounter in upstream oil and gas. We'll look at a wellhead separator, check valve reverse flow, and high pressure dump lines, like separators into low pressure tanks. So sometimes the need for a PSV is obvious. For instance, with the positive displacement pump, like piston, reciprocating, screw, vane, lobe, those types of pumps, you almost always require a PSV to protect itself and downstream piping. And sometimes the need for a PSV is not so obvious. So a centrifugal pump may or may not need a PSV. Just depends on the deadhead pressure of that pump, and of course the inlet pressure. So, in this case, you'd have to add the highest inlet pressure to the deadhead pressure, and if that was below the class 600 discharge piping, MAWP, then you may not need a PSV. So often a single PSV must be evaluated for multiple overpressure scenarios, and things can sometimes get pretty complicated. And I'd argue that when things are complicated, we tend to dig in deeper and pay more attention. So it's where we think the overpressure scenario is obvious, and I think that's where we need to pay, not take it too lightly and not overlook less obvious credible sources of overpressure, which can happen, and we'll get into an example of that. So how do we select a PSV and identify credible sources of overpressure? Well, it starts by identifying and defining boundary conditions. So, having a PFD and a P&ID is very helpful, well, almost essential in starting that process. Defining the system's pressure and temperature limits. So figuring out within that boundary condition, what's the weakest link? And then we need to define process conditions and and figure out what are we going to set this PSV's pressure at. So design basis memorandums, DBMs, heat material balance, operational data, they can all help define that set pressure. And then we need to identify for that node or that in that boundary condition, what are the credible causes of overpressure? At Landmark, we typically use what we call our API 521 checklist, and I'll get into that and why we use it and why we think it's important. And once you've identified all those credible scenarios or causes of overpressure, we need to figure out the relieving rates. And once you have that, you can figure out your orifice area required for each credible scenario. Okay, and then of course the largest required orifice for that node defines the governing basis for the PSV. And then finally we're ready to select a PSV for the governing case. So defining the boundary conditions. Here we've got a PFD for a typical compressor station. The things we want to look out for and where, like the boundary conditions for each PSV are spec brakes, vessels, pumps, compressors, control valves, bypass valves, outlet valves, heat exchangers. All those things help us define where we might need a PSV and where we define those boundary conditions. So all these different colored, what I call nodes on this PFD would require its own PSV and an evaluation of credible scenarios of overpressure. So how do we, or what is the weakest link in the node? Here we have a wellhead separator example. So the things we need to look out for, like if you have a line list, just defining the temperature and pressure limits of the pipe, all your valves, equipment, vessels, any heat exchangers that might be in play, and control valve details and pump and compressor curves will all be valuable when you're trying to decide if you need a PSV or not. One note is we need to be careful with pressure regulating valves, like for instance, a Fisher 627. Sometimes they can have tricky pressure limits on their internals. So you might order a valve that, it might be a class 600 or class like a threaded 3000 class valve. And you might think, oh, that thing's good for full class 600 pressure, but you have to be careful and dig into those manuals from Fisher sometimes and make sure that the internals are good for that pressure. So yeah, that's something important to remember. So defining the process conditions, the things you'll need, well, in upstream oil and gas or petrochemical, we often know like the fluid characteristics, well, in most systems really. So having gas or oil analyses, using process software like Promax or HYSYS can help you define condition or process conditions and properties, and online chemical databases can help you too. So we also need to look at rates, pressures, temperatures, and understand how the minimum, normal, and max rates can play into things. So sometimes you'll have a DBM or a heat material balance, and like here there's a trend where we had pressure and temperature for a full year. And we could really, this was an existing site that we're evaluating the case for a new PSV. So having operational data can sometimes help you refine the size of a PSV by using average rates or pressures, for instance, instead of maximum design values. So yeah, that can all come out in the detailed design of the PSV. So common causes of overpressure, like I mentioned earlier, API section 521, section 4.4 is a really great section in that document that identifies individual overpressure causes and their relieving rates. This is an example of our API checklist. Don't worry about reading all the causes, but essentially they identify about 16 or 17 different common causes in refineries, petrochemical, and oil and gas sites. The ones that we're going to deal with today are closed outlets, failure of control valves or automatic controls, and check valve failure and fire. Those are 3 or 4 of the most common ones that we see. So yeah, this checklist lets us do our due diligence and make sure that we've considered everything that we need to, and perhaps like not overlook something that we think is obvious, like I had mentioned earlier. So with that, let's jump into our wellhead separator example. So defining the boundary conditions, like I said in the earlier slide, things we look for are spec breaks. So here we've got a spec break where we're going from class 2500 to class 600. So we're something like 40,000 kPa going down to 9930 kPa. So there's a big spec break there. And so that's one thing we're looking for. We've got this vessel over here with 3 control valves, a back pressure control valve and 2 level control valves. So blocked outlet, you know, you could easily block this outlet. And we've got a vessel in play, and vessels not always, but almost always generally need a PSV of some sort. So in this wellhead example, defining the boundary conditions essentially are from that control valve, this inlet pressure control valve, over to the outlet valves here. So the next step is to look at that API checklist, and blocked outlet is definitely a scenario we can easily block the outlet of this node. We've got this pressure control valve that could fail. Its trim could wash out, especially on a wellhead. Choke valves, they can be subject to, you know, frac fluids coming back and sand, and so washing out a choke valve at a wellhead is not like a uncommon experience. And pool fire, we've got a vessel that has liquid in it that if there was a fire around the base of it, that could overpressure that vessel. So so let's just jump into each of these cases and see what API says about them and how we could solve or determine if it's credible or not. So blocked outlet, API defines as the inadvertent closure of a valve on the outlet of a pressure equipment while the equipment is on stream and can expose the equipment to pressure that exceeds the MAWP, or maximum allowable working pressure. Every valve, manual, control, or remotely operated, should be considered as being subject to inadvertent operation. And if the closure of an outlet valve can result in pressure in excess of that allowed by the design code, a PSV is required. Sometimes you'll see PRD, pressure relief device. PSV is probably more common, but yeah, that's just another acronym that you may see. So in this case, we have multiple valves that could block the outlet flow from the separator. And this system is fed by a 40,000 kPa wellhead, but its MAWP is 9930 downstream of that control valve. So can we overpressure the system? Well, sure. Like the obvious answer is sure. Our goal is to ensure that adequate safeguards exist to prevent overpressure. And generally, but not always, at least 2 safeguards are required to protect from overpressure. So we have this pressure control valve, which is controlling the pressure into this node. But depending on the code that you're working within or the process hazard analysis that you might perform, control valve cannot always be relied upon as a safeguard because it's doing a controlling function. So in this case, let's assume that we can't rely on this pressure control valve. We do have an ESD valve here. This ESD valve is tripped by a pressure switch high. So, you know, that is set to trip that ESD valve in case the pressure gets too high and the control valve isn't doing its job. So, or if you had an outlet valve. So that's a safeguard. And our PSV would be the second safeguard for this node. For the back pressure control valve, this guy or these 2 valves closing. But there's a little quirk in this node that we have these 2 manual valves between the spec brake here and the PSV. So if one of these were inadvertently closed, we'd lose access to that PSV as a safeguard. So you would either need to car seal these valves open or lock them open. Or if that wasn't possible, which isn't always possible, for instance, if you had multiple wellheads going into a group separator, you might not be able to car seal all those valves open. So in a scenario like that, you may have to break this node into 2 pieces upstream of these valves and have a PSV here. But let's assume for now we can car seal open these valves, and blocked outlet is a credible cause of overpressure for this PSV. So choke valve failure. If this choke valve or control valve failed to, if it's, like I said, if it's trim washed out, it would cause a sudden increase in flow capacity in an overpressure scenario, potential overpressure scenario. So that we do have this ESD valve that closes with a high pressure switch as a safeguard. So that is still in play, like for our block flow scenario. And the PSV would be a secondary safeguard or a second safeguard. But yeah, so in this case, we were defining choke valve failure as a credible cause of overpressure for that PSV. But like nothing in life, or I would say engineering, is ever absolute. And there may be times when designing a PSV for choke valve failure or any control valve failing really is not reasonable. And what do I mean by it not being reasonable? Well, the choke valve trim may be too large, like that, because of the pressure differential across that. And if the choke valve trim was too big, you might end up with a PSV that's just unreasonably large. And so if you're dealing with an existing constraint like a flare system, maybe that PSV can't be tied into your existing flare system because it would overwhelm it, or maybe the vessel didn't come with that, like that size of PSV, and you need to put a new nozzle on there, which nobody would want to do, like if you didn't have to. So, you know, what are some of the options that we could look at to mitigate the size of that PSV, or could we or eliminate choke valve failure as a credible scenario? Well, there's a couple ways we could do that. One would be to, sorry, I'll just go back here. Like if that choke valve trim was too big, if it wasn't, you could potentially reduce the trim on that control valve, and if it still met your operational conditions. Like we come across that a lot where control valves are just way oversized, and when you start digging into it, and operations are like, oh yeah, like we do have trouble controlling that valve sometimes on normal flow because it might be too operating, say, less than 20% open. So sometimes if the valve is too big, you could reduce the trim, and reducing the trim size of that control valve would, you know, reduce the rate at which it would, you know, that you could flow across it if it failed open. So that's one thing you could consider. If that wasn't an option, well, maybe we could add a second ESD valve to protect against choke valve failure. This would normally require independent pressure switches, or, you know, transmitters. So like a transmitter for each ESD valve so that they're independent. The pressure sensing is independent of, you know, for each ESD valve. So that could be an option. But if you do rely on dual ESD valves, or the ESD valve, any ESD valve, there's a problem that if it's failing and you trip it at a pressure, that valve, it doesn't close instantly. So depending on how fast this valve closes actually dictates how much the pressure, like how fast that pressure will rise. And so you might have to do a pressure or a process safety time calculation. So that's a dynamic model typically that determines how fast an ESD valve must close so that you don't reach the MAWP of that vessel. So in this scenario, the time to reach overpressure, so in a PST calc, the time to reach that overpressure depends on a few things. The first one is the pressure set point, or pressure switch high set point. So the closer your high pressure switch is to the MAWP of the system, the less time you'll have available. We talked about the CV of the valve. So, you know, the CV of the valve is directly related, like it's almost directly proportional to how fast you're gonna essentially fill up this downstream piping, and then how much volume is available in that downstream piping and the vessel itself. So the bigger that separator is, the more room there is and the more time you're going to have to close that ESD valve. The piping is usually pretty negligible. Like you might have a 3 or 4 inch pipe feeding this separator. So the vessel is usually the more dominating factor in that volume. So here's a sort of a hypothetical process safety time calc. And I guess convincing ourselves that we don't need a PSV in a system, sometimes it's referred to as overpressure protection by system design, like in ABSA, OPPSD. I like to say is like, can we math our way out of that PSV? And so here's a couple like two curves where this blue curve, this line is the MEWP of the system. It's 10,000 kPa, and our first case is where we shut down at 6,000 kPa. So we have a pressure shutdown there, and you could see that in this system it takes 3 seconds before we hit that MEWP. So we'd have to ensure that that ESD valve closes less than 3 seconds so that we don't overpressure that downstream piping. And you can see if you're setting your pressure shutdown high at a more typical value, say like 90% of the MAWP, well, that, you're reducing in this example, you're reducing that time to overpressure by almost 6. So like from 3 seconds to a half a second. So yeah, you can play with, sometimes you can play with that pressure shut down high, and sometimes you can't. And getting a valve to close really fast, like in half a second, it's possible, but standard valves generally don't close that fast. So you'd have to be careful with the ESD valve that you choose and understanding how fast it can actually close to protect the system. So like these bullet points here say, yeah, you may be able to math your way out of it. You may not, depending on the ESD available and the practicalities of the system. So I think like my preference is always not to sort of math your way out of a PSV and to size the PSV for choke valve failure when reasonable, but you can't always do that, and sometimes you have to look at alternatives. And if you were to do this, you'd have to really be careful and evaluate safeguards for their adequacy, which typically involves a HAZOP or some kind of process hazard analysis study, just to make sure that, yeah, like you might require a HIP system, which is a high integrity pressure protection system that, yeah, it kind of opens a bigger can of worms. Then you might want to go down. So yeah, I think that's all on this slide. And then the third credible scenario that we have for this separator is fire. Yeah, most vessels will require PSV for fire unless they're greater than, say, 20 feet above grade. So you see that in petrochemical plants a lot with multiple floors, and if stuff is high above grade, then you might be able to not put a PSV on for fire. But yeah, sometimes it's hard to like register a vessel if it doesn't have a PSV even. So sometimes the path of least resistance is just to have a PSV on a vessel anyways. PSVs for fire dependent on the surface area of the vessel. So, wellhead separators are typically not that big, maybe 3 feet diameter by 8 or 10 feet high, or even 2 foot diameter. So their fire, the sizing for a fire PSV is generally pretty small. But then when you get into bigger vessels like inlets, like free water knockouts, or treaters, like an 8 foot by 40 foot vessel, then your PSVs start to get really big. And sometimes you might even need 2, depending on the situation, just because your orifice sizes get so big. So as a summary, for this wellhead separator, we've identified blocked outlet, failure of the choke valve to control pressure, and wool fire as credible scenarios. And once we've done all our math and figured out the rates, the required rates for each of these scenarios, that's this column, you can see that our, well, hopefully you guys can see this, but the text is maybe a bit small, but our closed outlet requires a flow rate of 2 million standard cubic feet per day and an orifice area of 0.045. So that puts us into a D orifice. Our choke valve failure in this scenario is nearly 7 times the blocked flow rate and bumps us into an F orifice. So yeah, that, so far that's our biggest area required. And then, like I said, this is a wellhead separator, so its fire requirement, its area required for fire is actually quite low. That would put us into a D. You could probably even, yeah, put this down to a C orifice, which are less common, but so the governing scenario in this case is the guy with the biggest area required. And so on this particular example, we would need an F orifice PSV. And just, this was more for another presentation, but just be careful when you're looking at orifice sizes because there's two definitions. There's an API orifice size, so as you can see here, and an ASME orifice size, and they're slightly different. So if you had picked an F orifice with the API standard, you'd be pushing right up against the, using the full area of that PSV, which, might make me a little nervous to, did I get this right? Do I have 2% wiggle room? Or, an F ASME is a slightly bigger area and could give you, a little more uh, wiggle room, like 16% excess capacity, where, yeah, you're using a little less of that area. So that's something to note if you're picking a PSV and defining which type of orifice that you want. So yeah, in this case, I think this was mostly based on a real example. We ended up putting an F ASME F orifice in there for that PSV. Yeah, I don't know if there's any questions yet. Doesn't look like it. Feel free to ask questions as we go here. You can put them in the chat. So another common scenario we run into is check valve failure or leakage or misdirected flow. So in this case here, we've got like a header here, and it looks like they're trying to dump some, class 300 lower pressure stuff into this higher pressure header. Yeah, you might ask yourself, like, what the heck are they doing here? Why are they doing this? There's many reasons why someone might do this. Yeah, like, and we see it all the time. Like, you might have a lower pressure piece of lower pressure equipment that you're trying to use, and you're trying to get into a higher pressure system. Operationally wise, maybe they never operate this higher than 600, class 600. So maybe that's why they did that. But the problem is that check valves are almost guaranteed to leak. Yeah, API even says that you can't rely on check valves for overpressure. So if only one check valve is in play here, we would have quite a large PSV potential here. And essentially, if this was a 2-inch check valve, you would have to assume you have a 2-inch, diameter orifice and calculate how much flow could go back through that if it had failed. And generally that'll end up being quite a large PSV. So just
Craig, is that we have a question.
Okay.
Uh, can you see it on this Q&A, or would you like me to read it?
For API versus ASME orifice sizes, is there a scenario where a certain one must be used per code? I don't think so. Like we've seen sites, ASME B31.3 site that uses both kind of orifices. So I don't think there's a rule for B31.3 that you need to use ASME orifices. I think it's just more user beware that you ensure that you know which one you're getting, and because yeah, I think the safe assumption, if you don't know what you're getting or you don't know what's being installed, is assume it's the lower one, so the API size, and then you'll have a little conservancy built in. But yeah, hopefully that answers your question. So other solutions to protect against check valve failure. Look back here. So what about eliminating the hazard? Like, I think, yeah, design everything upstream on that class 300 side to class 600, but that's not always possible. But in a perfect world, that's what you try to do so that you eliminate the hazard instead of managing your way out of it. Double check valves are a way to reduce the size of that PSV. So like it says here, if you do have dual check valves, they want you to have different types. So, if they both would have different failure mechanisms. So the idea is that you reduce the likelihood of both failing simultaneously. The leakage rate, yeah, if you do have dual check valves, like it says here, you can assume that you have an orifice that's 10% of the full pipe size. So typically that results in quite a bit smaller PSV. And sometimes a PSV just isn't practical. Maybe there's no flare close by, nowhere to take those liquids or gas to. So that could be a reason why you don't want to use a PSV. Other solutions to protect against check valve failure. Well, here, this is kind of similar to what we talked about with the choke valve failure, but using dual ESD valves that are tripped by independent pressure sensors could be used to eliminate the PSV potentially. Um, Obviously, well, not always obviously, but when someone sees two control valves and two pressure switches, like most project engineers will see dollar signs or project managers. So it's probably going to be more expensive than just putting in dual check valves and a PSV. But if you don't have anywhere for that PSV outlet to go, then maybe this would be a solution. Again, you'd have to consider process safety time calc. So, how fast these guys have to close before you fill up this system and overpressure it. That would be an important consideration to make. And if it was a liquid system only, you might, and you slam those valves too close too fast, you could create water hammer and introduce a whole new issue that you didn't have before. So, this isn't always a solution, but it could be. And when you do propose things that you're saying you don't need a PSV for, it opens you up to more scrutiny by regulatory bodies. Could require high HIP systems like we talked about earlier. And yeah, sometimes depending on auditors you get, like in Alberta with ABSA, um, yeah, sometimes things go smoothly and sometimes it opens a can of worms. And yeah, so doing stuff where you're mathing your way out of, you just have to make sure you have all your I's dotted and T's crossed and that you've done your due diligence engineering wise. And I would
Craig, we
say,
have another question.
okay, let me look here. Double pressure protection is a requirement under ASME. Can double check valves plus a PSV be the two forms, or would it? Yeah, I think that would, yeah, so could double check valves plus a PSV be the two forms of protection, or would it require an ESD or other form? I think, in my opinion, the PSV is the reliable means of protection. But generally you'd want to do a process hazard analysis because depending on like a HAZOP facilitator or the sort of rules and standards of the company that you're working with, you may need something else. But in our experience, like dual checks and the single PSV is generally enough. And reduces that likelihood in a risk analysis. So hopefully that answers that question. Yeah, these last points here, often codes or regulations will allow deviations from best practice, like say using a PSV with appropriate engineering justification. If you do go that path like we're talking about here, it's generally best to do a HAZOP or process hazard analysis to ensure that you're lowering that risk level appropriately and understanding the nuances of the regulatory body you're dealing with. Like Mitchell in the chat said, B31.3 wouldn't, like sometimes B31.3 won't allow you to use a pressure control valve as a safeguard, but CSA actually does allow you. So in that wellhead example, it can get fuzzy. So understanding the nuances of, whatever code you're designing to and regulatory body you have to deal with is important. And I'd just say like the codes often give you enough sort of rope to hang yourself or get yourself in trouble. And yeah, so sometimes we have to do that, and it's just part of the nature of the game we're in. But yeah, PSVs are the easier, cleaner solution often. Okay, we got one more example here, and this is a pretty common example, a blocked outlet scenario. So say we've got a high pressure class 600 separator dumping into a low pressure drain header and into an atmospheric tank. A common solution to prevent anyone from closing this outlet valve is to lock it open or car seal it open. So this ensures a free path to the tank, and essentially, as long as your tank venting is designed properly, that this shouldn't cause an overpressure scenario in this piping. So car seals are an administrative control, and anyone who's been in a safety meeting or a HAZOP has probably seen this hierarchy, but even API 521 sort of reiterates it, that protective measures should be in this order. Eliminate the risk altogether, engineering controls, or administrative controls. So how could we do this system better? Well, if you're designing a greenfield site, why not just eliminate the risk altogether and build your whole drain header all the way to your tank inlet 600 ANSI or class 600. That way someone could close this and there's no potential for overpressure in that system. That's one way to do it. Yeah, I guess, yeah, that's just something to keep in mind. Like, how can you eliminate that risk altogether? And that check valve example, similarly, like why, if you see that on a site, you're often asking yourself, what the heck were they thinking here? Why did they do that? But there's usually a reason it was done in the past. But yeah, just note that if you have the chance to eliminate a risk in your design, that's a better way to go. Yeah, and just summarizing things up here, some final thoughts. You know, nothing in life, or I would argue engineering, is absolute. Just because it was done before doesn't mean it was right or will work this time. We've been involved with a lot of projects with clients who are replacing PSVs that are reached end of life, say, like it was installed 15, 20 years ago. And yeah, the client, like often they just want to replace that PSV in kind, which is fine, but if there's no documentation on why that PSV, say, you know, oh, we've got an F orifice set at this pressure. If there's no documentation or no one has done an API checklist, you may be getting in trouble just assuming that that PSV was sized 20 years ago properly. So yeah, I would just say be cautious of those kind of scenarios, replacing in kind. And just because the PSV has been there for 20 years, like in a perfect world, it should have never opened, right? Like you should have pressure shutdowns and things that, you know, would have prevented that PSV from ever opening. So yeah, I think this is an important note, like, and not just with PSVs, but a lot of things that we deal with in facilities. Yeah, these are just a few of the more maybe common examples we run into. Of course, there are many more. Yeah, I'd say like at Landmark, we always try to complete an API checklist when we're dealing with PSVs. It helps us, you know, perform our due diligence and make sure we've considered everything. And that way, if, you know, if you pass this project to somebody else or back to your client, like they can be confident that everything has been considered. And yeah, and reviewing those API checklists, I think I mentioned earlier with operations and, you know, the guys that are at site and know the site better than anyone, that's super important. Sometimes you can eliminate a cause of overpressure just with like local knowledge of that facility. So, oh yeah, that's my next bullet point. Get client input, super important. That knowledge of their systems is critical to ensure all things are being considered. And, you know, often HAZOPs or PHAs are essential in everything we do, especially with, yeah, these protecting ourselves from essentially, you know, worst case scenario, blowing things up. So that is the last slide. Just, yeah, open it up to if anyone has any more questions. Feel free to put it in the chat. I'm not sure if you guys can unmute yourselves or not, but
Also, if you want, feel free to, is that you can send an email to Craig direct or to myself, and that we'll make sure that you get a response and that can continue that dialogue. So is that Danielle, to your point, yeah, is that I'll go and Landmark does have a YouTube channel now, and that I will be posting it on YouTube, and I can send you the link if you want to share that. Great. Just wait. We have a few questions in the chat here. I'm just switching over to.
Yeah. Just let me open the chat there.
So, yeah, just as far as sharing, absolutely, and that. So, Craig, thanks again for this. Is that our next webinar is that it's going to be May 4th, and we're going to give Craig a break, and we're going to jump into pipeline integrity on May 4th, and into level 3 defect assessments. So Craig gets a break, and hopefully I'll send an invitation out, and you join us on May 4th.
Great. Thanks, Mitch, for organizing this and everyone for your attendance.
Okay. Have a great day, everyone. Thank you.
Thank you. Bye.